All we will wait for 4 5 minutes. See if anyone joins, then we will start. Good evening to all. My name is Ganesh Shankar Bhandari, and I am a PMRF research scholar and a teaching assistant for the course Principles of Extractive Metallurgy taught by Professor Tarun Kumar Kundu, IIT Kharagpur. So I am here to take the live sessions for the last week lectures of the NPTEL course. So first we will start with the revision of the last week lectures. Then we will go with then we will go with some MCQ type or numerical problems, which will help you to solve the assignment problems of for this week lectures for this course. Okay, so in the previous week lectures, we learned about the different types of fuels and how they behave, like GCV values and of calorific values of those fuels by Dulong's calculations of those values by Dulong's formula there, how to analyze the physical and chemical properties of coal or any fuel source by the by using proximate analysis and ultimate analysis. So now we will talk about the metallurgical coke and how to form that metallurgical coke with the help of the coking coal, and the design and components of and the byproducts recovered during the coke making process, and the operation and procedure of coke ovens, how the strength and of the coke tested after the manufacturing process of coke, then mass and CV balance in coke making. So the coke is an important secondary fuels in metallurgical industry. Significantly, generally when we talk about the blast furnace operations, so we cannot go with the coal as a fuel source. We have to go with the coke, and for making coke, we have to prep, we have to take the coking coal through some procedures to make the coke for blast furnace operation. Coke is the source of chemical and thermal energy with sufficient strength to withstand the load of overburden and permeability for flow of gases ascending upwards in the blast furnace. So what is the major difference between this coal and coke is that the strength of the coke is much better as compared to the coal. So we can use this in the blast furnace operations, and the plasticity of the coke is much better than the coal material. Then the metallurgical coke is the production of coke is happened with the help of the coking coal in the absence of air at 1000 to 1200 degrees Celsius for 14 to 20 hours in byproduct coke oven, which yields a strong and porous carbonaceous mass. And this process is called carbonization or destructive distillation of coal. So, what happened during this procedure? Any type of volatile material, any amount of volatile material present in the coking coal will get decreased, and the plasticity of and strength of the coke is getting increased during this whole process. So coal is charged batch-wise into silica-lined retorts, which are heated indirectly. Like externally, we are heating them by burning mostly coke oven gas, which is also a byproduct of this coke making process. And the volatile matter from the coal is collected in the byproduct recovery plant, where they are separated into pitch, benzene, toluene, naphthalene, ammonia, and H2S gases. So during the coke making process, we are getting coke as a main product, and as a byproduct, we are also getting some pitch, benzene, toluene, and naphthalene gases mixture, which can be directly reused as a fuel source for during the coke making operation itself. So, byproduct coke, if we talk about the dimensions of this byproduct coke oven, this method involves heating a coking coal held in relatively thin section, which is around 0.35 to 0.6 meter long, 0.35 to 0.6 meter thickness, and 11 to 13.5 meter long, and height is around 2.7 to 6.5 meter. Which is called as coke chambers or retort, which are made up of silica, which is having very high thermal conductivity and alkali resistance. In absence of air, we are not providing any air during the heating operations from either side by two heating chambers. The charged coal beds get converted into coke after being heated for 14 to 18 hours at 1200 degrees Celsius temperature. And the hot coke is pushed out, cooled, sized, and used for the further operation. Byproduct coke ovens, they can produce 16 to 20, 16 to 20 tons of coal can be charged at one time, and are used mainly for producing metallurgical grade coke. So the narrow width helps in fast cooking rate and temperature uniformity. The poor thermal conductivity of coal limits ovens width. So if we are going with the width more than 0.6 meter, it will not be feasible for the coke making operations because of the poor thermal conductivity of the coal. So the major components of byproduct coke ovens are coking chamber, which can have 40 to 60 batteries simultaneously, and the heating chamber. Then regenerators are there, which are used to separate the heat from the coking from the byproduct gases generated during the coke making operations. Then self-sealing oven doors, coal charging from top charge or stump charging can be there. Then pusher car, gas collection and treatment unit, and then at last coke quenching unit. So the major process during this coke making operation is the quenching of the coke. We have to quench the coke immediately. after discharging from the coke ovens for creating the strength and maintaining the properties which we want in the cokes. So this is a typical diagram of this byproduct coke oven plant. Then coke oven properties. The production of a top charge by product coke oven involves four steps. Coal charging in oven, then bed labeling, coal carbonization on oven, and pushing out coke from the oven after the 12 to 14-hour time period gets completed. In stamp charge coke oven, the stamped green coal cake is pushed in the oven through pusher side door, and the coal bed labeling is not required. So undergoes following changes during the coke making operations, like from 0 to 300 degree when the temperature is going to increase from 0 to 300 degrees Celsius. The evolution of moisture and volatile matter will take place. Then 400 to 500 degrees Celsius. The plastic mass present in the coal will get converted and will provide the strength to the coke. Then conversion of plastic mass to semi-coke, and then at last from 600 to 1200 degrees Celsius, the semi-coke will get converted into the coke material, which will be having very high strength, so that it can be used as a feed material during blast furnace operations. The two adjoining chambers are never charged or discharged in sequence, as this will cause heavy thermal demand from adjoining heating chambers, causing fall in oven temperature and damage to refractory. All the charging and discharging is done keeping a good gap 3 plus sequence. Then coming to the post after the coke making process, we have to check the properties of the produced coke, so that we can analyze if that coke can be reused as a feed material in blast furnace operation or not. The coke is tested for its ability to sustain impact and wear actions by two different tests. One is Satter test, which is used for checking the impact strength of the coke, and then there is tumbler test, which is used to calculate the wear strength of the coal. So during the Satter index test, a drum is used which is having 1000 mm diameter and 1000 mm wide, fitted with four lifters and with each having 400 mm size. And this drum is rotated at 25 RPM for 100 revolutions. And we are putting a size range of -75 to +50 mm size range. So Saturn index will be calculated as the weight of coke surviving bigger than 50 mm divided by 22.7 kg of coke which we are charging inside this oven plus 50 mm size into 100. So that will be known as our Saturn index. While calculating the MICOM 40 or MICOM 10 index, we will go with the formula weight of coke retained on 40 mm screen divided by 50 kg initial weight into 100. So with the help of these formulations and testing procedures, we can calculate the Satter index and MICOM M40 or M10 index of the coke. Then modern pre-carbonization treatment, the coal charge bulk density decide the coke quality and oven productivity. Bulk density is modified by selective coal crushing, coal preheating, coal briquette blending, or coal stamping. So that thing we can. So selective coal crushing is done in like two stages. First, from -3.2 mm with minimum zero point 0.2 mm fines. Uh, then coal preheating is done up to 300 degrees Celsius before charging the coal inside the coke oven battery. And coal briquette blending is takes place. The coal fines are compacted to briquette, adding tar and pitch and blended partially with fine coal. And then we are going to charge these coal briquette inside the coke charging ovens to create the coke. Then coal stamping that is done with the help of -3.2 mm size, which is compacted using 10% around 10% moisture to prepare a compact coherent mass, which can be handled as a green cake and put in the oven from the pusher side to produce the coke with the help of coke oven batteries. So if we talk about the mass balance in coke making and charging value, so there is a numerical is given. A byproduct coke oven uses coke coal and produces coke tar and coke oven gas. As given in the diagram, calculate amount of the coal required to make 1 ton 1000 kg coke, percentage of sulfur distributed in coke from coal, and percentage of heating value of the coal obtained on burning coke, amount of coke oven gas produced. So, with the help of mass balancing, we can calculate all these things, like whatever the input we are giving in the coke oven, that will be equal to the output which we are getting. So, input will be the coal, and the output, as we can see, output is going to be the coke, tar, and coke oven gases. So, whatever the amount of coal, as we can see, the amount of carbon present in this coal is around 7. If we talk about carbon mass balancing, so the amount of carbon present in coal is around 76%. While when we are going to produce when we are going to produce the coke material, so the amount of carbon inside the coke material is getting increased from 76 to 85%. And then tar is having a carbon amount of 89%, and some amount of carbon will also be going to be present in the coke oven gases. So if we are going to create a mass balance of carbon, so mass balance of carbon will be like carbon present in the coal material will be equal to the carbon present in the coke, tar, and carbon and coke oven gases. So with the help of this mass balancing, we can calculate all the things. Then standard temperature. Okay, okay. Then coming to the next lecture. So now we will talk about the combustion process. So combustion is the high temperature reaction between oxygen and combustible substance like carbon and hydrocarbons, oil, and natural gases, giving flame with release of intense heat and light. So combustion process is like a exothermic process, which we can define as a reaction between the any fuel and oxygen gas. It can provide some exothermic reactions to produce the high temperatures like 500 or 600 degrees Celsius, or whatever temperature we want to achieve. We have to provide the fuel quality according to that, fuel quality and quantity according to our requirement. If we want to create a temperature of around 2000 degrees Celsius, then we have to increase the quantity of the fuel provided and the oxygen provided into the system. The products of combustion, POC or flue gases, essentially consist of oxides of the constituent in fuel. Like if the fuel consists of carbon, sulfur, and hydrogen, so the product, or we can say products of combustion, will be like CO or CO2, and hydrogen can produce H2O, and sulfur can produce SO2. So products will be like the combination of compound and the oxygen. Complete conversion of reacting carbon and hydrocarbon substances to carbon dioxide and water vapor with full release of its thermal energy is known as the complete combustion. While incomplete combustion is known as products of combustion contain some amount of carbon monoxide or unburned fuel. So, like if our fuel is producing 100% CO2, okay, then we can say the fuel has been completely combust down. While if it is having some presence of CO, or we can say carbon monoxide in the products of combustion, then the combustion has not completed properly, and it will be known as the incomplete combustion process. So for creating a complete combustion process, what we have to do, we have to provide the proper amount of the oxygen during the whole combustion process, so that it can get so the carbon or hydrogen present inside the fuel can get converted into the CO2 and water vapors H2O. The complete as we can see, the complete oxidation of hydrogen will be like it is going to get converted into H2O. So if water is going to condense, then it will create energy of around 572 kilojoule. If water is still present as a steam, so it will create an energy of around 484 kilojoule per mole. The complete oxidation of carbon will be like C plus O2 equal to CO2, and it is going to produce energy of 394 kilojoule per mole. The incomplete oxidation of carbon is going to produce energy of 221 kilojoule per mole. The aim of the plant operator is to obtain a steady heat release at the rate required to suit the process objectives with complete utilization of heating value of fuels. So already we have talked about what we are going to provide the oxygen content and the fuel quality and quantity inside any furnace or inside any reactor according to our heating requirement. What temperature we want to achieve in that particular reactor. Uh, on the basis of that, we are going to provide the feed inside that particular reactor. So fuels and O2 air is properly mixed or require excess O2 air supply. Solid fuels are pulverized to expose more surface for combustion, and liquid fuels are atomized for better combustion. So if we talk about fuel to air ratio, so theoretical or stoichiometric air ratio is like the minimum air supply necessary to react with the fuel for complete combustion and generates energy content in it to the greatest extent will be known as the theoretical or stoichiometric air requirement for the complete combustion of the fuel. So if we talk about if we talk about a fuel having this formulation CH4 plus 2, uh, so CH4, we are trying to combust down the methane gas, and we are trying to combust this methane gas in the presence of the air. Okay, so the theoretical air requirement for the complete combustion of this methane gas is going to be like CH4 plus 2O2 plus 79 divided by 21N2, and this CH4 is going to get converted in during the complete combustion process. It is going to get converted into CO2 and the water vapor, and the N2 will not get react with anything because N2 is going to dissociate only if we are increasing the temperature more than around 1400 or 1500 degrees Celsius. So uh, the complete requirement according to calculations, the complete fuel to air stoichiometric requirement on the volume basis will be like 1 meter cube of CH4 is going to require around 9.52 meter cube of the stoichiometric air for the complete combustion of the methane gases. So actual air supply or fuel air may not be the same as stoichiometry. We always have to provide more than the stoichiometric amount of air for the proper combustion of the fuels. So it has to be like more than the stoichiometric requirements, like 1.10x of stoichiometry or 1.2x of stoichiometry, that we have to check. So, combustion non-stoichiometric mixtures, so it is like vice versa to the stoichiometric mixtures. If we are not going to provide the proper stoichiometric amount during the combustion process, or we don't want proper, or we can say complete combustion of any fuel source, so we will not provide the stoichiometric or excess amount of air for the complete combustion. So it will be known as the non-stoichiometric mixtures. Then flammability, okay. Then excess air and combustion efficiency. So we have already talked about we required at least stoichiometric amount of air for the complete combustion of the process. However, in the practical processes, it is not possible to completely combust any fuel with the stoichiometric amount of air. So we always provide some excess air amount for the complete combustion. So theoretical complete combustion is obtained by stoichiometric amount of air, and POC should not contain CO. But in actual combustion of any fuel does not occur with just stoichiometric amount of air. So statistically, the probability of finding N2 in the neighborhood of carbon is more than O2. The required excess air is the extra amount of air supplied over theoretical air to complete the combustion of the fuel. So mixing determines combustion or thermal efficiency. That is the ability of a device used for mixing of fuel and air to convert potential energy of fuel into thermal energy. So combustion efficiency equal to thermal energy obtained divided by potential energy of fuel in calorific value into 100. So generally we go with the 5 to 10% of the excess air for the proper combustion of the any natural gas, while in fuel oil it can increase up to 5 to 20%, while in case of solid fuels it can go up to 5 to 60% also as a excess air. Increasing excess air gets reflected in flue gases as free oxygen and extra nitrogen. So whatever the uh, because oxygen is going to get combustion into stoichiometric amount only. So whatever the extra excess amount of oxygen we are or excess amount of air we are providing to the system, it will reflect in our flue gases. So total or actual air in combustion, the total or actual air supplied for combustion is the sum of theoretical air and excess air requirement. Poor combustion efficiency leads to wastage of fuel, environmental and workplace pollution, and obviously it is expensive to run because we have to provide extra amount of air inside the furnace, or uh, we need to go for extra extra we need to give extra efforts during the mixing processes of these fuels. So the actual air used for combustion is generally divided into two or three parts. One is primary, then secondary and tertiary air to ensure its full utilization for complete combustion of fuels. Okay, so it is okay. Now we have talked about the characteristic of the coke. Now we will talk about the liquid fuel characteristics. In the coke making process, or when we were talking about the solid fuels, we talked about proximate analysis, we talked about ultimate analysis, and we can go for density and other things also. While in liquid fuel analysis, we have to determine the some more chemical properties of that liquid fuels like flash point, fire point, auto ignition temperature, cloud point, or pour point. So flash point is defined as the lowest temperature at which oil gives sufficient vapor, which offers a momentary flash on exposure to a standard flame in air. It is a measure of fire risk of oil stored or transported in oil tanks. So it is like when we are transporting, so we will provide some extra pressure on the liquid so that it cannot get react with the air and it cannot get vaporized. Okay, so it after evaporation it can get out from the oil tanks or whatever in the or the stored tanks, storage tanks. So that thing we have to kept in mind. Then for fire point, it is the temperature at which oil will continue to burn for at least 5 seconds after ignition by an open flame. The fire point is like little higher than around 10 degrees Celsius higher than the flash point. Then auto ignition temperature or spontaneous ignition temperature is it is the minimum temperature required for igniting gas or vapors in air without a spark or flame. Then cloud point is defined as when oil is cooled at specified rate, it becomes hazy or cloudy due to separation of wax crystals at some temperatures, to be termed as cloud points. Below this temperature, oil viscosity will get increased and it may clog filters. Then coming to the pour point, the pour point is the lowest temperature at which oil becomes semi-solid and the oil's flow is retarded or viscous due to the formation of wax crystals. The pour point is 3 degrees Celsius higher than the temperature at which oil ceases to flow. So if we talk about this cloud point, okay. So the perfect example for this cloud point is like difference between the automobile fuels. When we talk about automobiles fuels, we talk about this. Diesel and petrol. And we when we talk about the jet fuel, okay, so the difference between this jet fuels and automobile fuels, diesel and petrol is is the difference between their cloud point. Okay, because if we are going to use the same diesel and petrol oil in the jet engines, okay, that is not going to work due to uh, because when we are talking about the height. Okay, so the temperature and pressure at that particular point will get increase or decrease. Due to that, the oil viscosity will get changed, and due to the change in that particular oil viscosity, we going to we are not going to get the efficient combustion of that particular fuel. So in that thing we have to keep in mind to design the fuel source for different temperature conditions. Okay, like if we talk about the countries which can get a temperature in temperature of around -30 or -40 degrees Celsius during winter season, then then we have to design the fuel source according to that only. While in if we talk about Africa, then the temperature will be at around 40 or 45 degrees Celsius during summer sessions and 30 degrees Celsius during the winter sessions. So according to that, we can design our fuel source what we want to according to the temperature conditions. So determination of POC composition or ORSET analysis. The ORSET operator consists of a calibrated water jacketed gas burette connected by glass capillary tubing to 2 to 3 pipettes containing absorbents like potassium hydroxide for CO2, alkaline pyrogalol for O2, and ammonical cuprous chloride by the means of ORSET. What is the ORSET analysis? This ORSET analysis gives actual analysis on a dry basis for a fuel source. The common ORSET gives volume percentage of O2, percent CO, percent CO2, N2, and the SO2 amount present in a fuel source. Okay, okay. And coming to mass balance in combustion and theoretical air and excess air requirements. So material and heat balance in combustion. Material balance is used to calculate what amount of air or oxygen that can be theoretical or excess required for a composition and amount of fuel. Then amount of product of combustion and its composition uh, by using theoretical POC or excess air, whatever we are going to use. Then excess air when composition of POC is known, reading from offset analyzer, then amount of air leakage not given during combustion from POC amount and composition. Then heat balance calculation to determine temperature attained by POC or flame temperature. Then in the heat balance, we generally calculate it at 298 Kelvin as a reference temperature. Then the amount of heat input equal to sensible heat in air plus sensible heat in fuel plus heat release on combustion. That is calorific value for complete combustion from reaction enthalpy. Then we can calculate the amount of heat output that is going to be a sensible heat in POC plus heat loss on dissociation of POC. So sensible heat in air will be defined as the mass of O2 into ST air minus enthalpy of that particular compound at 298 Kelvin, then mass of N2 into ST air minus S298. Then we can calculate sensible heat in fuel and sensible heat in POC according to that only. And based on this, we have a for. So we have given a furnace uses coal analyzing is using a fuel source which analyzes 72% carbon, 4% hydrogen, and other things are also there, and 13.2% S on dry basis. So we are providing this fuel composition on the dry basis. The air used for complete coal combustion contain 20% excess air. So we are providing around 1.2x of stoichiometric air requirement. Then calculate per ton 1000 kg of coal per ton of coal combustion, the theoretical air required in meter cube at STP, then volume of actual air used in meter cube at STP, and amount of dry flue gas and its percentage analysis and offset analysis of that particular fuel source. So when we are going to calculate this thing, so first thing we have to do when we are talking about the proper combustion or complete combustion of the process. Okay, so we will go for the stable oxide states of the particular elements present in the fuel source after the combustion process. So like carbon is going to get converted into the CO2 and H2 is getting converted into the H2O, while N2 will remain as N2O. O2 is going to get react during the whole process, then sulfur is going to get converted into the SO2. So according to the 1000 kg coal and mass percentage, we can calculate the amount of particular elements present in a fuel source. Then we can convert them into their respective molecular weight, and according to the combustion reactions, like C plus O2 is going to change into CO2, while H2 will react with 1 mole of H2 is going to get reacted with only 0.5 moles of oxygen. and it is going to get converted into the H2O, while 1 mole of sulfur is going to require 1 mole of oxygen for full combustion process to get converted into the SO2 amount. So according to that, we can calculate the amount of theoretical O2 required in kg per mole. Uh, then based on that, based on this thing, we can create the product of combustion like 60 CO2, 20 moles of H2O, and N2 is coming from N2 was not N2 was present in the fuel source itself, and it is also coming from the air which we are providing for the combustion process. So according to that, we can calculate the theoretical O2 requirement, and then as we have given, we are providing 20% excess air. So by multiplying 1.2 in the theoretical O2 requirement, we can calculate the excess air requirement. And then this dry flue gas analysis is going to be like this. Uh, and with the help of the standard enthalpy of formation, we can calculate the NCV, or total calorific value of the flue gas generated during the whole process. Then we have one more formula, one more numerical. A mixed gas contains 70% blast furnace gas and 30% coke oven gas was used in a furnace with excess air to get complete combustion. Okay, so now, in the previous problem, we were using coal as a fuel source. In this problem, we are going to use blast furnace gas and coke oven gas as a fuel source in a furnace. And we also have, that is understood thing, that we have to provide some excess air to get complete combustion of the fuel source. The flue gases analyzed 1.6% oxygen on gas dry basis. Calculate the amount of theoretical air per meter cube of mixed gas, then percentage excess air used, amount of actual air per meter cube. So the composition of this blast furnace and coke oven gases is given like this. So according to this composition, first we have to calculate the theoretical amount of oxygen required for the complete combustion of these elements. Okay, and then on the basis of this composition, 70% blast furnace gas and 30% coke oven gas, we can easily calculate the theoretical oxygen requirement for the complete combustion of this fuel source. And after calculating the theoretical combustion, we can go with the excess air calculation, and then we can after calculating the excess air, we can calculate the flue gas composition according to that thing. Okay, then coming to next lecture now, heat valence and theoretical adiabatic flame temperature. That is similar to this. Okay, heat valence, we can calculate according to the flue gas composition what the whatever heat is going to get generated. Then flame temperature calculation. The flame temperature is the highest temperature attained by the products of combustion when fuel is burned with air or oxygen. So method of flame temperature calculation, or we can say heat valence, is like sensible heat in air plus fuel plus heat of combustion equal to sensible heat in POC, product of combustion, plus heat losses from flame to surroundings. So it's like mass balancing process. Whatever the input we are providing will be going to be equal to the output. Okay, so the input will be the sensible heat in air and fuel, then heat of combustion, and the output will be like sensible heat in product of combustion plus some heat losses will be there from flame to surrounding, then heat absorbed due to dissociation of products of combustion. So there are some assumptions which we are going to take theoretical for calculation of the theoretical maximum adiabatic flame temperature. So combustion is adiabatic, and there is no loss of heat to the surroundings environment, and all of the energy released from combustion is used to heat the product of combustion only. The combustion is complete. POC are CO2, H2, and SO2, etc. Dissociation of POC is neglected. Then combustion occurs at constant pressure. So DH is going to be equal to CP delta T. So sensible heat in air plus sensible heat in fuel going to plus heat of combustion is going to be equal to sensible heat in product of combustion. So sensible heat in air plus sensible flame temperature calculations we can do according to this formulation. Then sensible heat CP values can vary for the different gases, like for CP for CO2 it is like 10.55 plus 2.16 into 10 to the minus 3 T. So the specific heat value of any product of combustion source is going to get changed is majorly dependent on the temperature at which we are going to create that combustion. Okay, so there are some formulations for empirical formulations for the CP calculations for then calculations of adiabatic flame temperature. There is some numerical. Consider the coal as given in example 1 is completely burned with theoretical amount of air introduced at 25 degrees Celsius. Calculate adiabatic flame temperature. Adiabatic flame temperature when 20% excess air is required. Adiabatic flame temperature when incomplete combustion takes place. Adiabatic flame temperature when incomplete combustion. So according to this combustion with theoretical amount of air. So we have already calculated the theoretical amount of air based on the complete combustion of the fuel source. So the flame temperature is going to be like. Okay, so on the basis of the theoretical amount of air with the help of combustion, we have calculated the product of combustions during the process, and we are taking the assumption that no sensible heat in air or coal is there. So flame temperature equal to T degree Celsius, and it can be calculated according to the formulation. Then combustion with 20% excess air of air. So the POC is going to get changed up to some point. Up to some point. So the POC, according to the new POC amount, we can calculate this adiabatic flame temperature. Then if we are talking about incomplete combustion with theoretical amount of air, so in the case of incomplete combustion, we will go with the carbon monoxide instead of the carbon dioxide. Okay, so based on that, we can calculate the adiabatic flame temperature, then air preheating with oxygen enrichment. Okay, we can easily calculate these things. Okay, then now we will talk about the furnace. So what is the furnace? A furnace is essentially a thermal enclosure and is employed to process physical or chemical. That process can be physical or chemical, whatever we are going to employ. Then to process raw materials at high temperatures to finish product in several industries. Like we can talk about heat treatment industry, we can talk about casting, we can talk about welding. Then the principal objectives of furnaces are to utilize heat efficiently so that losses are minimum and to handle the movement of different phases like solid, liquid or gaseous such that erosion and corrosion of the refractories are minimum. Because so why we need this refractories? Because we are talking about a temperature range of around 1000 to 2000 degrees Celsius. So for providing the proper efficiency during these furnaces, we have to go with the refractory linings during the furnace making processes. And heat is liberated by burning fuel with air or oxygen or from electrical energy to transfer to the charge. Some heat leaves with the hot product flue gases and through furnace opening and walls. So principal components of furnace are like first is heat generating devices that can be with the help of fossil fuel, and fossil fuel can be like your um, liquid or solid fuels. Like liquid fuels are diesel or petroleum oils, while we talk about the solid fuels, then we can use coke or coal or non-coking coal. Then electrical energy is there, so that can be done with the help of resistance heating or induction heating or arc heating. Then chemical energy, we can provide some exothermic reactions. Uh, with the help of those exothermic reactions, the temperature get increased. Then furnace enclosure are there, like refractory linings, thermal enclosure of the furnace provided by refractive bricks or linings. Refractive facing the thermal enclosure must have high refractoriness uh, and it has to be chemically inert in nature, whereas refractory facing the surrounding must have low thermal conductivity to minimize heat losses. Then heat exchangers are there. Heat exchanger to recover and reuse the heat of POC. It is installed either external to furnace or internal recirculation of POC within the furnace. So now instrumentation and control are there. Furnaces are equipped with various sensors and chemical and control panel display. Then gas movement system should be there by pressure generated by chimney draft or force draft due to use of blower. Then fuel utilization in furnace. As furnace is heated by the heat transfer from POC, both amount of heat generated and the temperature of source and sink are important. Heat transfer rate is proportional to the temperature difference between temperatures. The flame temperature must be greater than furnace temperature, and greater temperature difference ensures rapid heating of the furnace or whatever the object we are going to treat in that furnace. Higher flame temperatures uh, though increases the heat transfer rate, but it may cause overheating and destroy the lining of the furnace. For maximum heat utilization, POC must exit at the critical temperature where a process can be carried out. Heat carried away while leaving POC is not available. HPOC is equal to mass of POC into specific heat of POC into TPOC minus 298. Then available heat for processing is known as gross available heat, which is defined as a heat transfer by POC in cooling from its flame temperature to the process critical temperature. Okay. While net available heat can be defined as gross available heat minus some heat losses will be there in the during the furnace operation. So the net available heat can be calculated with the help of GAH minus whatever the heat losses is there. It can be used as a criteria for comparing the smelting or melting or heating efficiency of different furnaces. Then available heat for processing for a given furnace design and the daily heat demand required GAH is fixed per unit time basis. We can calculate fuel consumption equal to required GAH per unit time or divided by GS per kg of fuel. If heat supply is critical factor in determining the process throughout, then GH cannot determine the throughput. We have to consider the net available heat. So furnace throughput is going to be NAH generated per unit time divided by gross available heat per kg of fuel. So according to that, we can calculate the fuel requirement for operating any furnace according to our need. So X is air leakage, furnace draft, fuel to air ratio, sensible heat of reactant, POC exit temperature, incomplete combustion or unburdened fuel will control the fuel consumption during any heat treatment operation or fuel furnace operations. Uh, then heat recovery will be there. Efficient utilization of fossil fuel reserves requires utilization of heat of exiting POC from the furnace. So in this case, whatever the product of combustion is getting produced during any furnace operations. So we have to recover the heat from those POCs like flue gas. If we talk about, for example, if we talk about flue gases generated during the furnace operations. So those flue gases generally leaving the furnace with a temperature of around 600 or 700 degrees Celsius at least, or it can vary according to the furnace temperature. Like if we are talking about 2000 degrees Celsius furnace, then the flue gases temperature can be as high as around 1100 or 1200 degrees Celsius. Or if we talk about 1000 degrees Celsius furnace, then the POC released during the furnace can have a temperature of around 500 or 600 degrees Celsius according to the furnace temperature. So we for efficient operation of any furnace or the efficient utilization of any fuel source, we have to recover and reuse this heating values from the POC generated during the furnace operations. So for reusing and circulating this heat, we need to install some heat exchanger, or we have to internally recirculate that POC into the flame in the furnace itself. So what the heat exchanger will do, uh, the hot flue gases coming out from the furnace is going outside through the heat exchanger. So due to the temperature difference between the heat exchanger body and the flue gases. The flue gases are going to transfer the temperature from flue gases to the heat exchanger, and then again we can flow the cold air or cold input gases from those heat exchanger, so that that gas can attain that temperature before going to the furnace operations. So in that way we can utilize the heat carried out by these POCs, and these heat exchangers are generally known as the recuperators. Okay. So the operations of the regenerative heat exchangers involves the temporary storage of the heat transferred in a packing of high thermal capacity material. Here the hot and cold fluid pass through the same channels in the packing alternatively. Like when hot gases are passing through this chamber, so the hot gases will transfer the temperature to the recuperators, and then again alternatively when cold gases are passing through that same chamber, the you recuperators are going to provide that temperature to the cold gases. The hot fluid passes through the channels of the packing for a length of time, or we can say hot period, and the hot fluid is switched off. A reversal now takes place when the cold fluid is admitted into the channels of the packing for a length of time, at the end of which the cold fluid is switched off and another reversal occurs. So when we talk about mass and heat balance in any heat exchanger, so heat balance over an infinite simply small elements of length dx can be written at steady state. Heat lost by hot fluid equal to heat gained by the cold fluid minus heat loss from the element to the surrounding. So based on these things, we can calculate the uh, mass and heat balance in heat exchangers. Okay, so this is similar thing. So in heat exchange between hot flue gas and cold air, air cannot be preheated to the temperature above the flue gas temperature. Thus, there is a limit in efficiency. So efficiency limit will be defined as 100 into sensible heat in the air at hot flue gas temperature divided by sensible heat in hot flue gases. So relative efficiency is defined as the ratio of sensible heat of air at exit temperature and hot flue temperature. Thus relative efficiency equal to 100 into sensible heat in preheated air divided by sensible heat in air at hot flue gas temperature. So we get relationship between relative efficiency, overall thermal efficiency, and efficiency limit as relative efficiency equal to 100 into overall thermal efficiency divided by efficiency limit. So there are energy flow diagrams or Sankey diagrams based on which energy flow diagram is a specific type of flow diagram in which the width of the arrows is proportional to the quantity of energy. Length of arrows has no bearings with the quantity of energy. The input of energy begins from left of the diagram. The output of energy are shown on the right side of the diagram. These diagrams indicate the flow of energy in a process and help identifying the quality and quantity of energy, which are like temperatures of input and outputs of energy. So with the help of these Sankey diagrams, we can determine those things. Okay. So these were the previous week lectures. So now we will go with some numerical and MCQ type problems based on the previous week lectures. Okay. So the first question is, at what temperature range coke is produced in the coke ovens? So when we were talking about when we were talking about the byproduct coke ovens, so in the byproduct coke ovens, we were generally feeding the coking coal, or we can say caking coal inside the coke oven batteries, and we were treating it at around 1000 to 1200 degrees Celsius for 14 to 18 hours time period for producing the coke and byproduct gases, which consist of CO, CO2, some amount of H2 and SO2 will be there. So, and H2S, also H2S as a byproduct gas material. Okay. So at temperature of around 1000 to 1200 degrees Celsius, coke is produced in the coke battery byproduct coke battery ovens. So next process, which of them are the byproducts of the making of the coke making process? So when we talk about the byproducts, so benzene is produced as a byproduct, then ammonia gas is there, NH3, then naphthalene is there. So the answer is all of the above. So these were the byproducts produced as a flue gas during the byproduct coke oven batteries process. Then coming to next question, which test is used for determining the impact strength of coke? Tumbler test, Satter test, proximate analysis, or none of the above. So for determining the impact strength, we generally go with the Satter test for determining the strength of the coke which we have produced via the coke battery ovens. While the tumbler test is generally used for checking the abrasion or wear strength of coking coal. And proximate analysis is generally used for determining the volatile matter, moisture content, and ash analysis of any fuel source. So the answer is Satter test. Then coming to next question, coke compared to coal from which it has been made. It contains less volatile matter, it contains more carbon, greater percentage of ash. So, for example, we are talking about a coking coal, which is having 45% carbon, some 10% VM volatile matter, and then 10% ash content is there, and some amount of moisture is there. So, when we are talking about the coke making operations, so during the coke making operations, the volatile matter present inside this coke is going to get released in the gaseous form. Okay. So, what will happen now? The volatile matter content, the produced coke will be going to have less volatile matter. While according to the mass balance, the percentage of carbon is going to get increased, then the percentage of ash that is also going to get increased because during the process they are going nowhere. They are not going in flue gases or any other thing. The and only thing which is going to get released from the system is the volatile matter content inside that coking coal. And after that, it is going to get converted into the coking coke. Okay. So the answer is all A, B, and C. So volatile matter will going to be less, then more carbon content will be there, and the percentage of S will become higher. Match the following. So there is temperature range and changes during the coke making operation. So from 0 to 300 degrees Celsius, we talked about the different temperature range and the evolutions which are happening during the coke making process inside the coke oven batteries. So from 0 to 300 degrees Celsius, there will be evolution of moisture and volatile matter. Then 400 to 500 degrees Celsius. So there will be conversion of coal into a plastic mass. Okay, some volatile matter is going to get converted into the plastic mass. Then from 500 to 600 degrees Celsius, the conversion of plastic mass to semi coke will happen. And from 600 to 1200 degrees Celsius, this semi coke is going to get converted into the coke material, which is having higher strength compared to the coking coal material. Okay, so coming to next, match the following. So there are some chemical or we can say physical properties of the liquid fuels like flash point, fire point, cloud point, and pour point. So flash point, it is like, yes. So flash point, this is generally used for avoiding the fire risk, or we can say it is a measure of fire risk of oil stored or transported in oil tanks. In that case, we have to consider this flash point, because above this flash point, the material is going, the liquid fuel is going to get evaporated, and once it's started getting evaporated, so there are high chances that it can come into contact with the air or any spark, and that can start it to burn. Okay, then there is fire point. So the it is defined as, it is the temperature at which oil will continue to burn at least for 5 seconds. It will be known as the fire point. Then cloud point, it is defined as the, below this temperature, oil viscosity increases and it may clog filters. Then the pour points, it is like the lowest temperature at which oil becomes semi-solid. Okay. Then we have one numerical here. So methane, we are burning methane as a fuel source, which is yielding some carbon dioxide, which contains 20 moles of, and the feed contains 20 moles of CH4, 60% of O2, and 20% CO2, and 90% conversion of limiting reactant is achieved. Calculate the molar composition of the product stream using balance on molecular species. Okay, so we have a fuel source as CH4, and we are saying that we are creating around 90% of conversion of limiting reactant is achieved, while the feed contains around 20 mole percent CH4, 60% O2, and 20% CO2. So we have to calculate the molecular species in the product species. So we will go with the mass balancing process. So according to the problem, first we will create the input and output process. Okay. So if we are going according to the numerical problem, if we are going to if we are feeding 100 mole of the gas inside a furnace or whatever the reactor we are talking about, so it is containing 20% of CH4, then 60% oxygen is there, and 20% is CO2. Okay, and in the output section we are getting some moles of CH4, then O2 will be there, then CO2 and H2O. We don't know the amount, exact amount of these species which are coming outside from this system. So according to our full, if we talk about 100% efficiency burning, then we will go with the formulation of CH4 is going to get converted with the help of oxygen. It is going to get converted into CO2 and H2O molecules. But one thing is necessary here. We are achieving only 90% of conversion. Okay. So that thing we have to kept in mind. So now first we will go with like NCH4. We will balance the CH4 equation. So according to when we are talking about, in the input material, O2 is not going to convert it. O2 is just going to get participate in the reaction, while CO2 will remain as a CO2. So the only two things which are going to get converted into some other material is CH4, and O2 is going to get going to participate during the reaction for the proper combustion. So first we will go for the mole percentage of the CH4 which can be present in the output stream. So that we can calculate easily according to the 90% burning efficiency, and CH4 equal to so NCH4 equal to 0.100 into 20 moles of CH4 feed. The output will contain around 2 moles of CH4. Now we will go with the molecular balance. So we are left with 18 moles of CH4 for the burning operations. And this 18 moles of while if you talk about CO2 balance, so whatever the input we are providing, and that input is going to get converted into the output. On the other hand, some generation of CO2 will also be there according to the CH4 combustion. Okay, so according to that, we can determine our CO2 balance. So 100 moles into 0.200 moles of CO2 divided by mole feed plus 18 mole CH4 react, 1 mole of CO2 produce, 1 mole CH4. So the moles of CO2 which are going to present in the outside in the product scenario, that is going to be 38 mole of CO2. Now we will talk about H2O balance. Yeah. So one according to the calculations, 1 mole of CH4 is creating 2 moles of H2O in the product streams. So here we are talking about the burning of 18 moles of CH4 content. So this 18 mole of CH4 contains after the burning will produce 36 moles of H2O. While we talk about O2 balance, so according to the equation, 1 mole of CH4 was requiring 1 mole of oxygen for proper conversion of the CO2 and H2O material. So we have here 16 moles of oxygen. Okay. So 16 moles of oxygen, and then again according to our 18 moles of CH4 requirement, 18 moles of O2 is going to get burned during the operation. So we are going to left with only 24 moles of oxygen. So the amount, so now we can create the amount of this excess gas. So it is going to be present with like 2 moles of CH4, then 24 moles of O2 will be there, 38 moles of CO2 and 36 moles of H2O. So according to that, we can create the amount of the output gases. Then next question, a natural gas of an unknown composition is burning and the analysis of the product gas yields the following results. So now in the previous question, we were knowing the composition of the feed material. Okay, and then with the help of that feed material burning, we were trying to calculate the composition of the output gases. Now in this numerical problem, we don't know the composition of the feed gas. Okay, we have given the composition we have given with the composition of the output gases. Okay, so the scenario is same. Whatever the feed we are going to provide is going to get converted into the output. Okay, so the mass balance has to be on the same page. Okay, so we have given that product gas yields the following results with 0.130 mole of H2O, mole wet gas. Then offset analysis of flue gas is 1.5% CO, 6% CO2, 8.2% O2, and 84.3% of L2. So calculate the hydrogen to carbon ratio in the gas and speculate on what the gas might be. Okay. So now first we will try to uh, imagine our problem. Okay. So since the composition of the fuel is unknown, yes, level it is as though carbon and hydrogen were entering separately. Okay. So whatever the moles of hydrogen and carbon is going to get inside the fuel source, then it is going to get converted into either in CO, then it can convert into CO2 or H2O moles. Then we are also providing some air quantity because we can see here around 84.3% N2. So we are clear that we have to provide some excess air content, or we can say stoichiometric air content for the proper burning of that natural gas. Okay, so we don't know the quantity of molar quantity of these O2 and O2 and other things. However, we can calculate the quantity of the N2 because we know this natural gas is not going to contain any nitrogen amount inside that. Natural gas, it means like composition of CH4, or it can have some other hydrocarbons, but it is not going to have any nitrogen compound inside that. So with the help of this 84.3% N2 inside the flue gas, we can calculate the amount of N2, because the amount of N2 is directly going to get converted into the N2 in the flue gases. So from the given mole fraction of water QW equal to 100 mole dry gas, we have given 0.130 mole fraction of H2O. So we can calculate the molar balance of H2O. Okay, then now atomic carbon balance. When we talk about carbon balance, so carbon is going to either it is going to get converted into CO2, or it is going to get converted into the CO. So according to the reaction, we can calculate the atomic carbon balance. So that has to be around 7.5 moles of carbon for the proper requirement of this 1.5% CO and 6% CO2 inside the natural gas. Okay, so for creating 1.5 moles of CO, we need 1.5 moles of carbon. For creating 6.6 moles of CO2, we are going to need 6 moles of carbon. So the total carbon content will be at around 7.5 moles of carbon. Now we coming to the atomic hydrogen balance. So the hydrogen is going in two formations. One is H2O. Okay, so according to the based on that, we can calculate the amount of carbon, amount of hydrogen present in the natural gas. So it will be around 29.8 moles of hydrogen. Now, if we talk about the composition of natural gas, okay, so the natural gas is going to com composed of like hydrogen carbon ratio will be at around 3.97. So according to that thing, we can define our natural gas with a formula of around CH 3.97 and polymer fraction. So it can be like CH, we can consider it as a CH4, or we can consider it as a mixture of CH4 and other gases, so that it can create a mixture of this CH 3.97 N. Okay, so this is for today. Okay, now we can leave the meeting. Okay, thank you all for your presence.